There is a 110-foot mass of rock silently crossing the 1.46 million mile mark in deep space right now, moving steadily toward our orbital path. To the untrained eye looking at the mainstream tracking data, it is just another distant speck passing safely in the dark. But beneath that surface narrative lies a much more concerning mathematical reality. It is not the distance of today's Flyby that has planetary defense researchers watching the telemetry so closely, but the structural mechanism of the orbit it leaves behind. The danger isn't passing us, it is locking into place. The date on the calendar is June 9th. The object has a name that sounds clinical and forgettable. Asteroid 2026 KM3. It does not look like much in the images. A faint smudge of light, picked up by a telescope in the high desert, moving against a field of stationary stars. But that smudge is not small, and it is not slow. It is roughly 110 feet across, which is the height of an 11-story office building stood on end. It is moving at a velocity measured in tens of thousands of miles per hour, faster than any aircraft humans have ever built. And it is doing this in the cold vacuum of deep space, where there is no friction to slow it down, no air to warn us of its arrival, no sound at all. For most of the public, the story ends with one number, the closest approach distance. 1,046 million miles. That distance sounds enormous, and in human terms it is. It is roughly 6 times the distance from the Earth to the Moon. The mainstream press releases will use that number as a kind of reassurance, a safe pass, a near miss in the broadest sense of the phrase, the kind of headline that sits at the bottom of a news website for an afternoon and then disappears. But the people who actually study these objects for a living are not reading the press releases. They are reading the orbital element files. They are reading the radar astrometry. And in those files there is a much smaller number, one that almost nobody outside the planetary defense community ever talks about. That number tells a different story. It tells the story of where this rock will be in 10 years, and 20 years, and 50 years. It tells the story of a mathematical track now etched into the inner solar system, a track that will keep intersecting our orbit again, and again, and again. There are 3 honest ways to read the June 9th Flyby. The first reading is the public one. A harmless object passes at a safe distance, and the planet continues turning. This reading is technically true. The second reading is the institutional one. A potentially hazardous object is observed and logged, and its trajectory is refined for future modelling. This reading is also true, and it is the one that quietly drives the work at the Center for Near-Earth Object Studies in Pasadena. The third reading is the one almost nobody is talking about. The third reading is that this flyby is not the event. The flyby is the rehearsal. The flyby is the moment where Earth's gravity reaches out and gently nudges this rock into a closer, tighter, more permanent orbital relationship with us. That third reading is not conspiracy theory. It is not fringe. It is sitting in plain language inside the NASA Jet Propulsion Laboratory Small Body Database. It is sitting in the orbital element tables that any researcher can pull up on a public dashboard. It just does not make the headlines because it does not fit into a single sentence. Tonight we walk through exactly what NASA's radar is tracking, exactly what a 10 megaton airburst looks like, and exactly why the real threat from this rock is only just beginning. Before we go any further, if you enjoy what we do here at Rupture, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. The June 9th Pass. At exactly 1.46 million miles out, a piece of the early solar system is intersecting our neighbourhood. It has been travelling on this exact path for longer than human civilization has existed, and tonight it crosses the threshold that brings it closer to Earth than it has been in decades. The Catalina Sky Survey, operating from a mountaintop observatory north of Tucson, Arizona, first picked up the object designated 2026 KM3. The initial detection came as a series of faint pixel shifts on a wide-field camera, the kind of signature that the survey software flags automatically, and then sends down to a human analyst for confirmation. The analyst confirmed it within hours. A new object, roughly 110 feet across, moving on a heliocentric orbit that brought it inside the Earth's orbital path, designated 2026 KM3 according to the standard naming convention used by the Minor Planet Center in Cambridge, Massachusetts. That initial detection was only the beginning. Once a new near-Earth object is logged, the data is shared globally within minutes. Observatories in Hawaii, in Spain, in Chile, in South Africa all begin pointing their instruments at the same patch of sky. Each new observation gives the orbital math another anchor point, and with each anchor point, the predicted path of the object tightened. By the end of the first week, the orbit was constrained well enough to know that the rock would come close. By the end of the second week, the orbit was constrained well enough to know exactly how close, exactly when, and from exactly which direction. The number that emerged from that math is 1,460,000 miles. The date that emerged is June. The velocity that emerged is roughly 38,000 miles per hour relative to Earth. To put 38,000 miles per hour into a frame that makes sense, consider the fastest aircraft ever flown by human pilots. The SR-71 Blackbird cruised at just over 2,000 miles per hour. 2026 KM3 is moving nearly 20 times that speed. It is moving so fast that if it was skimming the surface of the United States, it would cross from the coast of California to the coast of Maine in under 5 minutes. It is moving so fast that the term moving almost feels too gentle. This rock is not drifting through space, it is tearing through it. The 1,460,000 mile distance places the closest approach point well outside the orbit of the Moon. The Moon, on average, sits about 239,000 miles from Earth. 2026 KM3 will pass at roughly 6 times that distance. The mainstream framing of this number is that it is a comfortable margin. There is no chance of an impact on June 9th. The orbital math does not allow for it. The error bars on the trajectory have been refined down to a level where the uncertainty is measured in tens of miles, not hundreds of thousands. That part of the story, the rock will miss on June 9th. But the deeper question is what kind of miss this is. In the language of orbital mechanics, a miss is not a single event, a miss is a relationship. When two objects pass each other at high speed in a shared gravitational field, the gravity of the larger object pulls on the smaller one. The pull is small in absolute terms, but the consequences of that pull are not small at all. The smaller object leaves the encounter on a slightly different orbit than the one it arrived on. Where it ends up on its next loop around the Sun depends entirely on the precise geometry of this single flyby. 46 million miles sounds vast to a human, but in orbital mechanics, it is the equivalent of a bullet grazing the fabric of your shirt. The rock is close enough that Earth's gravity tugs on it measurably, close enough that the tug changes its future path. Close enough that mission planners at NASA JPL are watching the data come in not because they are worried about today, but because they need to know exactly how the future just shifted. The June 9th pass is happening across a window of several hours. The exact moment of closest approach is calculated to a precision of about 30 seconds, based on the radar astrometry collected during the prior week. The rock will be visible to professional telescopes for a few nights around the closest approach, as a faint moving point of light against the background stars. It will not be visible to the naked eye. It will not be visible to backyard amateur astronomers with small telescopes. It is too small, too dark, and too distant. To see it at all, you need the kind of equipment that costs tens of millions of dollars and lives on top of a mountain. What you can see, if you know where to look, is the orbital diagram. The Center for Near-Earth Object Studies, known by the acronym NEOS, maintains a public dashboard at jpl.nasa.gov where the orbits of every catalogued near-Earth object can be viewed in 3 dimensions. Pull up 2026 KM3 on that dashboard, and you can watch the rock loop in from the cold outer reaches of its orbit, dip in toward the inner solar system, swing past the Earth-Moon system, and then head back out into the dark. It is a clean, almost elegant orbit, the kind of orbit that has been repeating for thousands of years. That orbit is what we need to understand. The numbers confirm it will miss us this time, but the physical reality of what just flew by requires us to look closer. Part 2. 110 feet of iron and stone. Picture an 11-story office building, forged from ancient iron and stone, hurtling through a vacuum at tens of thousands of miles per hour. That is the physical reality of 2026 KM3. Not a pebble, not a meteorite the size of a basketball. A structure roughly the dimensions of a medium-sized commercial building with a mass measured in the millions of pounds. The 110-foot figure comes from a calculation, not a direct measurement. We cannot measure asteroids of this size with a tape. They are too small and too distant to image directly with even our best telescopes. What we can measure is how much light they reflect. Astronomers measure the brightness of the object, called its absolute magnitude, and then they make an assumption about its surface reflectivity. Most asteroids reflect somewhere between 4% and 20% of the light that hits them. The darker rocks are mostly carbon, the brighter rocks are mostly silicate and metal. Without a direct radar bounce, the size estimate has a margin of error of plus or minus about 30%. For 2026 KM3, the best current estimate places the diameter at 110 feet, give or take a margin in either direction. That places it firmly in the size category that planetary scientists call city killers. Not big enough to threaten civilization on a continental scale, not small enough to burn up harmlessly on entry. Right in the middle, in the range where it would survive the atmosphere and do real damage on the ground. To put 110 feet into the context of the asteroid population, here is the scale. Every day, the Earth is hit by roughly 100 tons of cosmic material. The vast majority of that material is dust and pebbles, individual grains weighing fractions of an ounce, which produce the streaks of light we call shooting stars. A few times a year, an object the size of a basketball or a beach ball enters the atmosphere and produces a brief bright fireball. Once every few decades, an object the size of a car or a small truck enters the atmosphere, produces a daytime fireball, and sometimes drops fragments on the ground. These events are common enough that meteor showers are essentially weekly entertainment for serious sky watchers. At the other end of the scale, there are the planet killers. Objects more than half a mile across. These are the rocks that end geological eras. The dinosaur extinction event roughly 66 million years ago was caused by an object about 6 miles across. There are around 1,000 known near-Earth objects larger than half a mile across. Astronomers believe they have identified more than 90% of them. None of them are on a collision course with Earth in the foreseeable future. The middle category is where 2026 KM3 lives. Objects between roughly 65 feet and 500 feet across. These are not extinction-level rocks, but they are big enough to flatten a metropolitan area if they hit in the wrong place. Astronomers estimate that there are hundreds of thousands of objects in this size range crossing Earth's orbital neighbourhood. We have only catalogued a small fraction of them. The 2026 KM3 detection is one more name on a list that is growing every month, and the list is far from complete. The mass of a rock 110 feet across is hard to picture without grounding it in something familiar. A solid stone block of that size, if it were a simple cube, would weigh roughly 30 to 70,000 tons. Asteroids are not cubes. They are usually irregular, lumpy, and often partially hollow, with a structure that planetary scientists describe as rubble pile. But even on the low end of the mass estimate, 2026 KM3 weighs as much as several thousand fully loaded 18-wheel trucks combined. That mass by itself is not what makes the rock dangerous. The mass is what makes it persistent. A rock that big is not slowed down meaningfully by anything in the inner solar system. It is not deflected by solar wind. It is not eroded into nothing by the heat of the sun. It is too dense, too solid, and too massive for any of that. It just keeps orbiting. What makes the rock dangerous is the speed. A 110-foot rock moving at 38,000 miles per hour carries an amount of kinetic energy that is genuinely hard for the human mind to grasp. Kinetic energy scales with the square of velocity. Double the speed, and you quadruple the energy. The math, when you run it for an object of this mass and this velocity, produces a number measured in megatons of TNT equivalent. The mass of the rock isn't what causes the destruction. It is the sudden, violent deceleration of that mass hitting the upper atmosphere. When a rock this size strikes the upper layers of Earth's atmosphere, it does not gradually slow down. It runs into a wall of air molecules so dense that the air cannot get out of the way fast enough. The air compresses in front of the rock at enormous pressure. That compression heats the air to temperatures hotter than the surface of the sun. The rock itself starts to fracture. The fracturing releases enormous amounts of energy in a single catastrophic moment. That moment is what scientists call an airburst. An airburst is not an impact in the traditional sense. The rock does not necessarily hit the ground. It detonates above the ground, in the lower atmosphere, in a single violent release of energy that radiates outward in a shockwave and a thermal pulse. The destruction comes not from a crater, but from the wave. The wave flattens trees, shatters windows, knocks down buildings. and burns anything flammable within a wide radius below the detonation point. For a 110-foot rock entering at the speed of 2026 km/h, the airburst would be in the range of 5 to 10 megatons of TNT equivalent. That is roughly 300 to 700 times the energy of the bomb dropped on Hiroshima. It is also roughly the energy that the Federal Emergency Management Agency uses as its modelling baseline for the scenario we will walk through in Part 4. The point of running through these numbers is not to alarm. The rock is not going to hit us on June 9th. The point is to make clear, in plain language, what kind of object we are talking about. 2026 km/h is not a curiosity. It is not a distant smudge that drifts past and is forgotten. It is a 110-foot package of compressed energy moving on a path that crosses ours, and the only thing standing between today's safe pass and a future bad day is the precision of the orbital math. To understand how something this massive sneaks up on us, we have to understand how we are watching the sky. Part 3. The 1.46 million mile marker. Tracking a dark rock against a dark sky from over 1 million miles away requires specific, highly vulnerable instruments. That is the practical question that the people running the world's planetary defense network face every single night. And the answer is more fragile than most members of the public realize. The primary tool is the optical survey telescope. These are wide-field instruments designed to photograph large patches of the sky on a fixed schedule, comparing each new image to the previous one to spot anything that has moved. The Catalina Sky Survey in Arizona, the Pan-STARRS survey in Hawaii, and the Asteroid Terrestrial Impact Last Alert System known as ATLAS are the three workhorses of the American Detection Network. Together they discover the vast majority of new near-Earth objects each year. They are funded primarily through NASA's Planetary Defense Coordination Office, an office that was only formally established in 2016. An optical telescope sees an asteroid not as a glowing object, but as a faint moving dot. The rock itself emits no light. The only reason it shows up on the camera is because it is reflecting sunlight back toward Earth. That means the visibility of any given asteroid depends entirely on the geometry between the Sun, the rock, and the observer. Some geometries are favourable, and the rock shows up brightly. Other geometries are unfavourable, and the rock is essentially invisible. The most unfavourable geometry of all is the one where the rock approaches from the direction of the Sun. The tracking systems we rely on to sleep soundly at night have a massive, glaring blind spot pointing directly at our own star. When a near-Earth object swings in from the daylight side of the Earth, no ground-based optical telescope can see it. The Sun's glare overwhelms the camera. There is no contrast between the faint reflected light from the asteroid and the brilliant background of the solar disk. Astronomers call this the daylight sky problem, and it is the single biggest gap in our planetary defense network. There is no full solution to the daylight sky problem on the ground. The only solution is a space-based infrared telescope positioned somewhere out near the orbit of Venus, looking back at Earth from the inside. NASA has approved one such mission, the NEO Surveyor, intended for launch later this decade. Until that telescope is operational, the inside of Earth's orbit remains poorly monitored. The Chelyabinsk meteor of 2013, which we will examine in detail later in this script, came from exactly that direction. Nobody saw it coming until it lit up the sky over Russia. 2026 km/h, by contrast, was discovered well in advance. The geometry of its current orbit happens to favour optical detection. The rock approached from a direction that put it against the dark background of deep space, not against the glare of the Sun. That is what made the early detection possible, and it is also what made the subsequent radar follow-up possible. Radar astrometry is the second tool in the planetary defense kit, and it is far more precise than optical observation. The two great radar facilities for this work were Arecibo in Puerto Rico and the Goldstone Deep Space Communications Complex in California. Arecibo collapsed in 2020. Goldstone remains operational. The Goldstone Solar System radar bounces high-frequency radio waves off near-Earth objects and measures the precise timing and frequency shift of the returning signal. From that, planetary scientists can derive the asteroid's exact distance, exact velocity, and even some information about its shape and rotation. The catch with radar astrometry is that it only works at close range. The signal strength drops with a fourth power of the distance. That means a target 10 times farther away requires 10,000 times more transmitter power to produce the same return signal. In practice, radar can only image asteroids when they come within a few tens of millions of miles. For 2026 KM3, the radar window opens during the days leading up to the June 9th Flyby, peaks during closest approach, and then closes again as the rock recedes. This radar window is the most important data collection period for the entire encounter. Every observation taken during the flyby refines the predicted future orbit. Every refinement reduces the uncertainty about where the rock will be in 5 years, 10 years, 20 years. The data being collected this week, and the data scheduled to be collected over the next several days, will tighten the long-term trajectory predictions to a level of precision that was impossible just a few months ago. A solitary technician sits in a NASA JPL tracking room, staring at faint radar telemetry, pinging off a silent rock a million miles away, holding a cold cup of coffee while the rest of the world sleeps. The image is not metaphorical. There are exactly that many people doing exactly that job. In a small set of windowless control rooms in Pasadena, California, and in the antenna control building at the Goldstone site in the Mojave Desert. They work in shifts. They monitor signal returns that look like a smear on a waterfall plot, a frequency time diagram that shows the radar pulse coming back, slightly shifted by the Doppler effect, slightly delayed by the round-trip time. Every shift in the smear means something. Every delay means something. The technicians log the data, route it to the orbital determination team, and then go back to watching the next pulse return. It is not a glamorous job. It does not pay particularly well. The funding for the entire planetary defense coordination operation is a tiny fraction of NASA's overall budget, less than 0.5% in most fiscal years. The technicians who do this work are not famous. They do not get interviewed on television. They do not appear in documentaries, but they are the only thing standing between the silent geometry of the solar system and the unprepared population on the surface below. The fragility of the network is what most outside observers do not appreciate. There are fewer than a dozen sites globally doing serious asteroid detection work, supported by a single operational planetary radar facility and a handful of human analysts. A space-based infrared telescope remains entirely on the drawing board. The system works in the sense that it has detected and tracked thousands of near-Earth objects, including 2026 KM3. But the system has significant blind spots, limited capacity, and modest funding. It is a small, dedicated network watching a very large, very dangerous sky. We tracked 2026 KM3 in time, but to understand what happens when we don't, we have to look at the government's own disaster blueprints. Part 4. The FEMA megaton projections. 10 megatons of kinetic energy is not a theoretical number, it is a specific metric FEMA uses to plan for the unimaginable. The Federal Emergency Management Agency does not typically run drills for asteroid impacts. Hurricanes, yes. Floods, yes. Wildfires, yes. But every few years, FEMA and NASA jointly run a tabletop exercise that simulates exactly what would happen if a 2026 KM3 class object detonated over an American city. The most recent of these exercises was conducted in April of 2022 at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. The exercise was the 7th in a series that began in 2013. The 2022 scenario assumed a hypothetical asteroid roughly 230 feet across, slightly larger than 2026 KM3, on a 6-month warning trajectory toward Earth. The participants included senior officials from NASA, FEMA, the United States Space Command, the Federal Aviation Administration, and several state emergency management agencies. The exercise lasted 2 days. The results were sobering enough that the final report was published with a recommendation for significantly increased coordination across federal and state response agencies. The exercise modelled 2 specific impact scenarios in detail. The first scenario assumed a thermal dominant airburst over the Denver metropolitan area at an altitude of about 12 miles. The second scenario assumed a blast dominant airburst over the Winston-Salem area of North Carolina at an altitude of about 8 miles. The 2 scenarios were chosen to represent different geographic and infrastructure conditions: a high-altitude inland city with significant electrical grid exposure, and a mid-altitude city near a major power generation facility. In the Denver scenario, the thermal pulse from the airburst would deliver a flash of light and heat lasting roughly 30 seconds. The flash would reach intensities high enough to ignite dry grass, paper, fabric, and rooftop materials across a radius of roughly 30 miles. That ignition radius is larger than the Denver metro area itself. Anything flammable within line of sight of the detonation point would catch fire essentially simultaneously. The simultaneous ignition of tens of thousands of fires across a metropolitan region would overwhelm every fire department in the state within minutes. The local electrical grid, dependent on overhead transmission lines and rooftop equipment, would suffer cascading failures as transformers and switchgear were ignited or damaged by the thermal pulse. Within the first hour, the region would be in the dark. The thermal pulse from a 20 megaton airburst would ignite fires miles before the actual acoustic shockwave arrived to shatter the buildings. That timing is crucial to understand. Light travels faster than sound. The thermal flash arrives in a single instant, the moment of detonation. The acoustic shockwave, travelling at the speed of sound, arrives roughly a minute later for observers near the edge of the affected zone. That gap of a minute is when the fires start, before any windows have broken, before any walls have failed. By the time the shockwave hits and brings down the structures, those structures are already burning. The Winston-Salem scenario modelled a slightly different outcome. At a lower detonation altitude, the blast wave is more concentrated, and the thermal pulse is less geographically widespread. The result is a tighter zone of severe destruction. The FEMA model predicted total structural collapse within a radius of about 10 miles, severe structural damage out to about 25 miles, and significant window breakage and minor structural damage out to roughly 50 miles. The Belews Creek Steam Station, a coal-fired power plant operated by Duke Energy roughly 20 miles from downtown Winston-Salem, was modelled as suffering enough structural damage to force a complete shutdown of all generating units. With Belews Creek offline, the regional grid would lose roughly 200 megawatts of generating capacity in a single moment. That loss alone would trigger cascading blackouts across portions of North Carolina, South Carolina, and Virginia. The exercise then modelled the post-impact response window. The first 30 minutes would be dominated by sensor confirmation. Did this just happen? Was it really an asteroid? Or was it something else? The Department of Defense's space-based infrared sensors would pick up the thermal signature within seconds. NASA's NEOS office would cross-reference the location with its asteroid database. The confirmation would reach the White House Situation Room within 10 to 15 minutes. By the 30-minute mark, the impact would be officially confirmed and the Federal Emergency Response Apparatus would be activated. From there, the response would face a series of compounding failures. Local emergency communications would be down. Cell towers within the affected radius would be destroyed or unpowered. First responders within the impact zone would themselves be casualties. State emergency management offices in Denver or Raleigh would have minutes to issue evacuation orders before their own facilities lost power. The interstate highway system, which the response would depend on for moving aid and evacuating survivors, would be partially blocked by debris and abandoned vehicles. The exercise report estimated casualty figures in the range of tens of thousands to several 100,000, depending on the exact location and time of day. The economic damage was estimated in the trillions of dollars, factoring in immediate destruction, long-term grid repair, agricultural impact from atmospheric dust, and reconstruction costs spread over a day. The exercise did not produce a recommendation for evacuating cities. The recommendation it produced was much more sobering. The United States, as of the 2022 exercise, did not have a planetary defense capability that could meaningfully deflect or destroy an incoming asteroid with less than 10 years of warning. The Double Asteroid Redirection Test, called DART, conducted in September of 2022, successfully demonstrated that a spacecraft could alter the orbit of a small asteroid by kinetic impact. But DART was a single demonstration against a single target, with years of preparation time. Against a real incoming object with 6 months of warning, there is no operational system ready to launch. The Denver scenario, the Winston-Salem scenario, and the Goldstone radar tracking of 2026 KM3 are connected. They are all part of the same network of preparation, the same network of monitoring, the same network of quiet readiness for a day that statistically will eventually come. The exercise was not a science fiction exercise, it was a planning document. These projections sound like science fiction until you look at the historical record and realise it has already happened in our lifetime. Part 5. the 2013 warning. In February of 2013, the sky over Russia lit up brighter than the morning sun. The date was February 15th. The time was 9:20 in the morning, local Chelyabinsk time. The rock came in from the east, low across the horizon, on a shallow angle that brought it deep into the lower atmosphere before it broke apart. Thousands of people on their morning commutes saw the streak. Hundreds of dashboard cameras recorded the explosion. For about 30 seconds, the brightness of the meteor exceeded the brightness of the sun. The Chelyabinsk meteor was roughly 66 feet across, weighing in the range of 10,000 tons. It entered the atmosphere at about 42,000 miles per hour, slightly faster than the velocity of 2026 km/h. The angle of entry was shallow, only about 18 degrees above horizontal, which meant it travelled a long path through the upper atmosphere before disintegrating. The disintegration occurred at an altitude of roughly 18 miles above the ground, with a kinetic energy release equivalent to roughly 500 kilotons of TNT. 500 kilotons is approximately 30 times the energy of the Hiroshima bomb. The blast wave from that release propagated outward in all directions. It reached the city of Chelyabinsk, a metropolitan area of about 1.1 million people, roughly 90 seconds later. The wave hit the city as a sudden deafening boom, followed by a violent pressure shift that shattered windows across the entire region. The wave was strong enough to knock people off their feet, collapse partial sections of walls, and damage thousands of buildings. The Chelyabinsk rock was only 66 feet across, barely half the size of the asteroid currently flying past us, and it still put 500 people in the hospital. The official Russian government tally counted 1,491 reported injuries, the vast majority of them caused by broken glass. The shockwave shattered windows in over 7,200 buildings across 6 cities in the region. Roofs collapsed in several locations. A zinc factory in Chelyabinsk suffered the collapse of a wall, narrowly missing workers who had stepped outside moments earlier to see what the bright light in the sky was. The most striking detail from the medical reports is the pattern of injuries. The majority of the people hurt were standing near windows. They had been drawn to the windows by the bright flash 30 seconds earlier. They were looking up at the sky when the shockwave arrived. They were standing with their faces inches from the glass when that glass exploded inward. The cuts were across faces, hands, and chests. The injuries were predictable in retrospect, but in the moment, nobody knew to step away from the windows, because nobody understood what they had just seen. 2 facts about Chelyabinsk make it the single most important reference point for planetary defense. The first is the size. At 66 feet, the rock was at the low end of the city killer category that 2026 km/h sits in. The second fact, and the more troubling one, is the detection record. Nobody saw Chelyabinsk coming. Not NASA, not the Russian Space Agency, not the European Space Agency, not the Catalina Sky Survey or Pan-STARRS or Atlas. The rock approached from the direction of the rising sun. It was hidden in the daylight sky. Every ground-based optical telescope in the world was effectively blind to it. That detection failure was not a result of negligence or incompetence. It was a result of physics. The rock came in from the geometry that no ground-based telescope can see. The first time anyone outside the immediate Chelyabinsk region knew about the meteor was when the bright flash showed up on satellites, in dashboard camera footage, and on social media, all in the same instant. The detection lead time was negative. We learned about the rock by watching it explode. In the months after Chelyabinsk, NASA and other space agencies recalibrated their estimates of the asteroid population. The previous estimates had assumed that objects in the 60 to 100 foot size range were relatively rare in the near-Earth space, with one expected to encounter the atmosphere roughly once every 50 to 100 years. The Chelyabinsk event, combined with subsequent infrasound and satellite data collection, suggested that the actual rate of encounters with objects of that size is significantly higher. Current estimates place the rate at 1 encounter every 15 to 30 years. That revised estimate is what makes 2026 km/h historically significant. At 110 feet, the rock is larger than Chelyabinsk by a factor of roughly 4 in volume, and by a factor of roughly 6 to 8 in energy delivery. If a Chelyabinsk scale event happens every 15 to 30 years, then a 2026 km/h scale event happens, on average, every 50 to 100 years. That is roughly once per human lifetime. It is not common, but it is not rare either. The historical context becomes even more striking when you go further back. In June of 1908, an object of roughly 200 feet across exploded over the Tunguska region of central Siberia. The Tunguska event flattened roughly 800 square miles of forest, knocking down approximately 80 million trees in a radial pattern centered on the airburst. The energy release was estimated at roughly 10 to 15 megatons, almost exactly the FEMA modelling baseline for 2026 KM3 class events. Nobody died at Tunguska only because the location was uninhabited wilderness. If the rock had arrived 4 hours earlier or 4 hours later, it would have detonated over a populated region of either Europe or the Western Pacific. 3 events: Tunguska in 1908, Chelyabinsk in 2013, the unrecorded near misses in between. The historical record shows that the atmosphere has been absorbing impacts of this scale on a roughly century timescale, and every time the location was either an empty forest, an empty ocean, or a Russian industrial city that was sturdy enough to survive a 500 kiloton airburst with no fatalities. The next event of this scale will not necessarily benefit from the Chelyabinsk proved that our atmosphere doesn't protect us from these mid-sized objects, it turns them into atmospheric bombs. Part 6. The undetected angle. The most dangerous asteroid is never the one you are tracking on a public dashboard, it is the one hiding in the glare of the sun. The daylight sky problem we touched on in Part 3 is not just a technical inconvenience for astronomers, it is a structural blind spot in the entire planetary defense apparatus, and it is the single most important reason why a Chelyabinsk-scale event can still happen without warning. The geometry of the problem is straightforward. Earth orbits the Sun in a roughly circular path. An asteroid on its own heliocentric orbit can approach Earth from any direction in 3-dimensional space. If the asteroid approaches from the night side of the planet, it appears against the dark background of deep space and is relatively easy to detect with optical surveys. If the asteroid approaches from the day side, it appears against the bright background of the Sun and is essentially invisible to any ground-based telescope. The proportion of the sky that lies in the daylight cone is significant. Roughly 40% of the sky in any given Earth orbit position is either obscured by the Sun itself or by the bright daylight scatter in the surrounding angular region. 40% of the asteroid approach geometry is, in practical terms, unmonitored. Objects that approach from that direction simply cannot be detected by the current network until they are essentially on top of us, by which point any warning is meaningless. That gap is the reason the NEO-Surveyor mission exists. NEO-Surveyor is a space-based infrared telescope, scheduled for launch in 2027 or 2028 depending on budget cycles, designed to operate in a specific orbit between Earth and Venus. From that vantage point, looking outward toward Earth and the night side of the inner solar system, the telescope will see asteroids in infrared regardless of their position relative to the Sun. The mission's stated goal is to identify 90% of all near-Earth objects larger than 460 feet within a decade of launch, and to substantially improve the detection rate for objects in the 2026 KM3 size category. Until NEO-Surveyor is operational, the daylight blind spot remains. And the blind spot is not theoretical. The Chelyabinsk meteor came from precisely that direction. Several other near-Earth flybys in recent years, including objects in the 30 to 60 foot range, were detected only after they had already passed Earth, having approached from the day side. The detection record for objects coming from the Sun is essentially a record of after-the-fact discoveries. There is a more subtle version of the same problem, one that planetary scientists have begun to take more seriously in recent years. The question is whether some near-Earth objects travel with smaller companions. The basic physics says yes, this should happen. Asteroids in the inner solar system experience repeated gravitational encounters with the inner planets, and those encounters can shake fragments loose. A larger rock, on a stable orbit, can have one or more smaller pieces orbiting it loosely, or trailing behind it on slightly different paths. When the larger rock makes a close approach to Earth, the smaller companions come along for the ride, but they are not always detected. Gravitational wakes from larger objects can drag smaller, undetected fragments right through our tracking blind spots. The term gravitational wake describes the disturbance pattern that a massive object leaves in the gravitational field as it moves through a region of space. Smaller objects nearby can be pulled along in that wake, ending up on trajectories that are slightly different from the parent rock, but still in the same general approach direction. For tracking purposes, the parent rock dominates the radar return. The smaller companion, if it exists, can be lost in the signal noise. The probability that 2026 KM3 has an undetected smaller companion is low, but it is not zero. Most planetary scientists place the worst-case reading at 1 to 3%. That is the probability that a smaller fragment, perhaps in the range of 15 to 30 feet across, is trailing the main rock on a similar but offset trajectory. A 15-foot fragment is too small to be a Chelyabinsk scale event on its own, but it is large enough to produce a visible fireball and detectable infrasound, and it is large enough that its detection or non-detection has implications for our overall confidence in the network. The 1 to 3% number is not alarmist. It is a routine planning figure used internally at NEOs and similar offices. The vast majority of near-Earth objects do not have companions. The vast majority of close approaches are clean events involving a single rock. But the asteroid population is large, the observation capacity is limited, and the math allows for small companions to slip through. Every flyby is treated as an opportunity to look for that 1 to 3% case, both during the approach and in the days after the closest approach point. An early morning commuter in Chelyabinsk in 2013 scraped ice off their windshield in the freezing dark, just seconds before the sky detonated above them. That commuter, whoever they were, became part of the historical record without ever choosing to. They were not a witness in the traditional sense. They were a survivor of an event that had no advance notice, no public warning, no emergency broadcast. No time to step away from the windows. The dashboard cameras captured the moment in full. The video shows the morning street, the grey sky, the headlights of nearby cars, and then the sudden, overwhelming brightness that turned the morning into noon for 30 seconds. The commuter, in most of those videos, can be heard reacting in surprise and then in confusion. They had no framework for what they had just seen. That moment is the worst-case version of the daylight blind spot. The asteroid arrives without warning, the population is going about its morning, and the only protection is the random luck of where the rock happens to detonate. Chelyabinsk survived with broken windows and injuries because the airburst happened high enough and far enough from the city centre that the shockwave was diffused by the time it arrived. A few miles of difference in either direction, or a slightly different angle of entry, and the death toll could have been substantially higher. The lesson from Chelyabinsk is not that the system failed. The lesson is that the system, as it exists, is incomplete by design. We have not yet built the space-based infrared telescope that would close the daylight gap. We have not yet built the rapid response deflection capability that could meaningfully alter the orbit of an incoming object with less than 10 years of warning. We have a network that does good work within its limits. The limits are real, and the network is open about them. But the limits are also the part of the conversation that does not usually make the press. This constant game of cosmic hide-and-seek forces NASA to draw a very strict mathematical line in the sand. Part 7. The 150-meter threshold. The difference between a routine flyby and a planetary emergency is decided by a strict bureaucratic formula. That formula is not vague. It is not subject to interpretation. It is a specific set of two numbers that NASA uses to determine whether an asteroid receives a public warning, an internal monitoring tag, or no special attention at all. The two numbers are called the size threshold and the distance threshold. The size threshold is 150 meters, which converts to about 492 feet. The distance threshold is 0.05 astronomical units, which converts to roughly 4.6 million miles. An asteroid that exceeds both thresholds at any point in its predicted orbit is classified as a potentially hazardous object, abbreviated FO. An asteroid that exceeds one threshold but not the other is monitored but not flagged. An asteroid that exceeds neither threshold is logged in the database and otherwise left alone. The 150-meter size threshold was not chosen arbitrarily. It is the size at which an asteroid impact transitions from regional damage to potential global consequences. A 140-meter rock entering Earth's atmosphere would deliver an energy release in the range of 300 megatons to 1 gigaton, depending on its density and velocity. That energy release is large enough to produce continent-scale climate effects from dust and smoke injection into the stratosphere. It is also large enough to cause direct destruction across a region several hundred miles wide, regardless of whether the impact is on land or in the ocean. Below the 140-meter threshold, an impact would still be devastating to whoever happens to live near the detonation point. But the consequences would be regional, not global. A city or a metropolitan area could be destroyed. The surrounding agricultural region could be disrupted for years. The global climate, however, would not be measurably affected. The economic damage would be in the trillions of dollars, but it would be recoverable. Above the 140-meter threshold, the calculus changes. The impact begins to threaten food supplies in regions far from the impact site, atmospheric quality across hemispheres, and the long-term productivity of agriculture worldwide. Because 2026 KM3 is 110 feet instead of 492 feet, it avoids the most severe institutional alarms, even though it packs a 10 megaton punch. The rock falls well below the 150-meter threshold. It is, in the formal language of the Planetary Defense Coordination Office, a near-Earth object of interest, but it is not a potentially hazardous object. The distinction matters because the institutional response to a foe is dramatically different from the response to a non-foe. A foe gets a press release, a dedicated tracking team, and a place on the regular reporting schedule that the office sends up to NASA headquarters. A non-foe gets a database entry, a routine radar follow-up if available, and a quiet update when the data refines. The 4.6 million-mile distance threshold operates on similar logic. That distance is roughly 19 times the Earth-Moon distance. It is not chosen because anything within that distance is dangerous. It is chosen because anything within that distance is gravitationally interacting with Earth in a meaningful way. Objects that come within 6 million miles experience enough gravitational influence from Earth that their future orbits can be measurably altered by the encounter. Objects that stay outside that distance are essentially independent of Earth's gravity for the duration of the flyby. 2026 KM3 does cross the 4.6 million-mile threshold during the June 9th pass. The closest approach distance of 46 million miles is well inside the gravitational interaction zone. The rock is being measurably influenced by Earth's gravity right now, and that influence will leave a permanent trace on its future orbital path. That is the part of the calculation that the size threshold does not capture. By the strict formal definition, 2026 KM3 is not a foe, because it fails the size test. By the practical reality of orbital mechanics, it is exactly the kind of object that the foe designation was designed to flag. The mismatch between the bureaucratic categorization and the practical reality is not a flaw in the system. It is a deliberate choice. The foe threshold was set high in order to focus institutional attention and public communication on the rocks that pose the most consequential risks. There are tens of thousands of known near-Earth objects, and many more uncatalogued. The system cannot generate a press release for every flyby. The system cannot dedicate a tracking team to every rock that passes inside 4.6 million miles. The thresholds are a triage tool, and like all triage tools, they leave some cases on the wrong side of the line. 2026 KM3 is one of those cases. It is too small to trigger the foe designation, but large enough to deliver a 10 megaton airburst if it ever hit. It is on a trajectory that puts it within the gravitational interaction zone of Earth, but not on a trajectory that puts it at immediate risk of impact. It is, in essence, exactly the kind of rock that planetary defense scientists worry about quietly, behind the public communications, in the technical reports that few people outside the field ever read. There is a parallel debate ongoing within the planetary defense community about whether the 150-meter threshold is still the right number. Some researchers argue that the threshold should be lowered, perhaps to 100 meters or even to 50 meters, to better capture the city killer category of objects. Other researchers argue that lowering the threshold would dilute the institutional attention paid to the truly catastrophic objects and would also overwhelm the limited public communication channels. The debate has not been resolved, and the threshold has not changed. The international community, working through the United Nations-affiliated International Asteroid Warning Network, has maintained the current definition. In practical terms, that means 2026 KM3 will not generate a NASA press release about its flyby. It will not be the subject of a dedicated CNN segment. It will not appear on the front page of any major newspaper. It will be logged, tracked, and refined, and the data will be quietly published in the JPL Small Body Database, where anyone with an internet connection can look it up if they know where to find it. The rock will pass without fanfare, and the institutional record will move on to the next object. The size threshold dictates the public headlines, but the real danger is measured by a completely different equation. Part 8. The Hidden Threat. Earth MOID. Beneath the reassuring public statements, there is a hidden metric that planetary scientists care about more than anything else. The metric is called the Earth Minimum Orbit Intersection Distance, abbreviated as Earth MOID, and it is the single most important number for understanding whether an asteroid poses a long-term threat to our planet. The Earth MOID is a specific calculation. It does not measure where the asteroid is today, or where the asteroid will be on its next close approach, or where the asteroid will be at any particular moment in time. It measures something more fundamental than any of those. The Earth MOID measures the absolute minimum distance in three-dimensional space between the orbit of the asteroid and the orbit of the Earth, not the distance between the rock and the Earth at any moment, but the closest point that the two orbital paths can ever come to each other, regardless of where either object happens to be along its own path. To understand why this matters, picture two highways crossing in the desert. The highways do not always have traffic on them. Sometimes the highways are empty, but the point where the highways cross is fixed in space. If a truck is on Highway A and a car is on Highway B, and they happen to reach the crossing point at exactly the same moment, they collide. If their timing is even slightly off, they miss each other by a few seconds, and the trucks and cars continue on their way. The distance between the highways at their closest point is 0. The collision risk depends entirely on the timing. The Earth MOID is the cosmic equivalent of that crossing point distance. It is the geometric minimum between two orbital paths. When the Earth MOID is 0 or very near 0, the two orbits actually intersect in three-dimensional space. That means there is a specific point along both orbits where they share the same location. At that point, the only thing separating a flyby from a collision is the timing of when the Earth and the asteroid each reach the intersection point. For the vast majority of near-Earth objects, the Earth MOID is large enough that the two orbits never come close to intersecting. The asteroid passes by, sometimes at significant distances, sometimes at closer distances, but the underlying orbital geometry keeps the rock at arm's length. For a smaller subset of near-Earth objects, the Earth MOID is small enough that the orbits do, in some sense, share a region of space. For these objects, the question of whether they ever hit Earth becomes purely a question of timing. Are they at the crossing point when we are? The Earth MOID is calculated continuously for every catalogued near-Earth object. The number is recorded in the JPL Small Body Database. It is updated as new observations refine the orbital elements. It is one of the standard fields in the database, sitting alongside the orbital period, the eccentricity, the inclination, and the other basic orbital parameters. Any researcher, any journalist, any curious member of the public can look up the Earth MOID for any catalogued object in a matter of seconds. The press releases do not usually mention it. The mainstream news coverage does not usually explain it. The reason is not malice or cover-up. The reason is that the Earth MOID is a technical concept that takes more than one sentence to describe properly, and most news coverage operates on a one-sentence per fact budget. So the coverage settles for the closest approach distance, which is a single intuitive number, and leaves the Earth MOID in the database for the specialists to discuss among themselves. That choice is understandable from a communications standpoint. It is also a choice that systematically obscures the most important risk metric. Closest approach distance tells you what happens this time. Earth MOID tells you what happens every time, forever, until the orbit changes. For an asteroid like 2026 KM3, with an orbital period of a few years, that distinction matters profoundly. The rock will keep coming back, every few years, on a path that crosses ours. Each pass will be at a different distance, depending on the precise timing of where Earth is along its own orbit when the asteroid arrives. Earth MOID proves that the threat isn't the rock passing us today. The threat is the invisible orbital track it leaves behind, waiting for us to cross it again. The track is permanent. The track does not erode. The track does not fade away after the flyby. It sits in the inner solar system, a geometric loop that crosses Earth's loop at one or two specific points, and every time Earth comes around to the crossing point. The question of whether the asteroid is also there determines the outcome. There is a further wrinkle that makes the Earth MOID even more important. The Earth MOID is not static. The number can change over time as the asteroid's orbit is perturbed by gravitational encounters with Earth, with the Moon, with Venus, with Mars, with Jupiter, and with the more distant planets. Each gravitational tug subtly alters the orbital elements. The orbit shifts. The MOID number changes. Sometimes the change makes the MOID larger, pushing the rock onto a safer track. Sometimes the change makes the MOID smaller, pulling the orbit closer to ours. The flyby on June 9th is one of those gravitational tugs. The encounter with Earth's gravity will alter the orbit of 2026 KM3 by a small but measurable amount. The post-flyby orbit will not be quite the same as the pre-flyby orbit. The Earth MOID number after the flyby will be slightly different from the Earth MOID number before the flyby. Whether the new number is smaller or larger depends entirely on the precise geometry of this single pass. The number sitting in the database right now is the pre-flyby value. The post-flyby value will be calculated from the radar astrometry collected over the next several days, refined over the next several weeks, and finalized over the next several months. That number, whatever it turns out to be, will determine the long-term threat profile of this specific rock. Once you see the exact MOID number calculated for this asteroid, the June 9th flyby stops looking like a relief and starts looking like a countdown. Part 9. The mathematical collision risk. The number sitting quietly in the Center for Near-Earth Object Studies database right now is 0.012641 astronomical units. That is the current Earth MOID value for asteroid 2026 KM3, as recorded in the JPL small body database before the post-flyby refinement. The number is precise to 7 decimal places. It is not an estimate, it is a calculation, based on the orbital elements derived from the optical and radar observations collected since the rock was discovered. To translate that number into something more intuitive, 1 astronomical unit is the average distance from the Earth to the Sun, roughly 93 million miles. 0,1264412 astronomical units is therefore about 1.17 million miles. That is the absolute minimum distance, in 3-dimensional space, between the orbit of 2026 KM3 and the orbit of Earth. 1,017 million miles is closer than the 46 million mile flyby distance for June 9th. Let that fact sit for a moment. The closest approach of the rock on this specific pass is greater than the closest approach the 2 orbits can ever come to each other. That means, in principle, the 2 orbits get closer at some other point. If the timing were slightly different, if 2026 KM3 had reached the crossing point a few weeks earlier or later, the closest approach would have been measurably tighter than today's number. The future passes of 2026 KM3 are not guaranteed to come close to the MOID. The rock has an orbital period of roughly 3 to 4 years, depending on the precise orbital elements after the flyby. Each pass, the rock returns to the inner solar system on a new arrival schedule, and Earth is in a different position when the asteroid arrives. Most passes, the rock and the Earth will be far apart at the crossing point. Some passes, the rock and the Earth will be closer. And on rare passes, the 2 will be close enough that the flyby distance approaches the MOID number itself. A fractional change in the gravitational pull from Earth today can bend that MOID value closer to 0 for the next decade. That is the technical phenomenon known as a gravitational keyhole. A keyhole is a very specific region of space, narrow in cross-section, where if an asteroid passes through it during a close approach, the gravitational interaction with Earth produces an orbital deflection that places the asteroid on a future collision course. The keyhole metaphor comes from the idea that the asteroid has to thread the needle of a very narrow corridor in order to be put onto a colliding orbit at a later date. Keyholes are real. The mathematics is straightforward. The orbital mechanics community first formalized the concept in the early 2000s after the discovery of an asteroid named Apophis, which was found to have a 2029 close approach that included passage near several keyholes for later impact dates. The Apophis case has since been refined, and the rock is now believed to pose no significant impact risk for at least the next century. But the keyhole framework, which was developed to analyze Apophis, has become a standard tool for assessing the long-term risk profile of every catalogued near-Earth object. For 2026 KM3, the keyhole map is being updated continuously. The pre-flyby calculations identify the regions of space near the closest approach point, where passage would produce a significantly altered post-flyby orbit. The radar astrometry being collected during the flyby refines the rock's position relative to those keyhole regions. The post-flyby radar data, scheduled to be collected over the next several days, will determine whether 2026 KM3 actually passed through any of the keyholes, and if so, what the new orbital elements look like. The elevated reading from the pre-flyby calculations places the probability of significant orbital alteration at somewhere in the range of 8 to 12%. That is not a probability of impact. That is the probability that the post-flyby orbit will be different enough from the pre-flyby orbit to warrant a full recalculation of the future impact risk timeline. In most cases, the recalculation will show that the new orbit moves the MOID further from Earth, not closer. In a smaller subset of cases, the recalculation will show that the new orbit moves the MOID closer to Earth, with implications for impact risk on subsequent passes. The exact distribution of outcomes is not a secret. The CNEO's team publishes the analysis after the radar data is processed. The publication is in the form of a technical update on the JPL website, listing the new orbital elements, the new MOID value, and the new probabilities for future close approaches. The update is not announced with a press conference. It appears on the database with the date of the most recent observation appended, and the planetary defense community reads it and adjusts its planning accordingly. A grid operator sits at the controls of the Belews Creek steam station in Winston-Salem, completely unaware that their facility's long-term survival relies on a 0.0126412 decimal point holding steady in the dark. The operator is doing their job. They are monitoring transmission line voltages, watching for trips in the substations across the regional grid, coordinating with neighbouring utilities to balance load and generation. The operator has never heard of 2026 KM3. They have never opened the JPL small body database. They do not know what an Earth MOID is. They are not paid to know. But the FEMA 2022 exercise put their facility on a list. Belews Creek was one of the explicit case studies in the airburst modelling for the Winston-Salem scenario. The exercise concluded that a 110-foot to 230-foot asteroid airburst over the Winston-Salem area would force a complete shutdown of the plant for an indefinite period, with cascading consequences for the regional grid. The operator's facility was named, by name, in a federal exercise report. The operator does not know this. The operator's supervisor probably does not know this. The information is sitting in a planning document that exists primarily for emergency management professionals, not for the people who actually run the infrastructure. That is not a criticism. The communication system between federal planning and infrastructure operations works on a need-to-know basis. The operator does not need to know about asteroid risk to do their job. The asteroid risk is so low on any given day that telling every infrastructure operator about it would be pointless and counterproductive. The risk is real, but it is distributed across decades, and the day-to-day work of running the plant is shaped by much more immediate concerns: weather, equipment failure, fuel supply, demand fluctuations. The risk, even so, is there. The 0.0126412 number is sitting in the database. The Belews Creek facility is sitting in the FEMA modelling document. The two are connected by a chain of mathematical and physical reasoning that has been laid out in detail in a series of technical papers, exercise reports, and database entries. The chain is long, and the probability per year is low, but the chain is intact, and it does not break apart just because the public conversation does not include it. The math is undeniable, which is exactly why the internet has already started to weaponize it. Part 10. What this isn't: the Armageddon narrative. If you spend 5 minutes looking at social media, you will find people claiming the government is hiding an extinction event scheduled for this Tuesday. The claim is not new. It is a recurring pattern that emerges around every well-publicized near-Earth object close approach. The pattern follows a predictable arc. A real asteroid is detected. The real orbital data is published on the JPL website. A real news story appears, summarizing the flyby distance and the size estimate. And then a wave of social media accounts seizes on selected pieces of the real data, removes the context, and constructs an alternative narrative in which the rock is on a collision course and the government is concealing the truth. The 2026 KM3 flyby has produced its own version of this pattern. The viral claims circulating online include several specific assertions. The first assertion is that the rock will not actually miss Earth on June 9th, and that the published flyby distance of 1.46 million miles is a deliberate fabrication. The second assertion is that the FEMA 2022 exercise was not a planning exercise, but a rehearsal for a known incoming impact. The third assertion is that the Earth MOID value of 0.0126412 astronomical units proves that the rock will hit Earth within days. The fourth assertion is that government agencies, including NASA and FEMA, are preparing for a specific impact on a specific date and have already begun moving senior officials to secure facilities. Each of these assertions takes a piece of real data and applies it incorrectly. The flyby distance is not fabricated. It is calculated from observations made by dozens of independent observatories around the world, including private institutions and foreign government agencies that have no incentive to coordinate a fake number with NASA. The FEMA exercise was a planning exercise with publicly available transcripts and an after-action report posted on the FEMA website. The Earth MOID value does not predict impact within days. It describes a geometric minimum distance between two orbital paths over long timescales. The reports of secure facility preparations are unverified and, in the specific cases that have been checked by independent journalists, traced back to misidentified routine maintenance schedules. The conspiracy theorists are using real NASA data, but they are applying the long-term orbital math to a short-term timeline. That is the core of the misreading. The Earth MOID is a real risk metric. It does describe a meaningful geometric relationship. It does have implications for impact probability, but it operates on timescales of decades and centuries, not days. A close MOID does not mean an impact this week. It means a possible impact at some point in the future, when the timing of the orbit and the timing of Earth's position happen to coincide at the crossing point. The honest version of the risk story is more boring than the conspiracy version, but it is also more troubling in its own way. The rock, the flyby, and the Earth MOID number are all documented facts. The FEMA modelling, historical events like Chelyabinsk, and the daylight blind spot represent confirmed realities, just like the severe budget constraints placed on the Planetary Defence Coordination Office. None of these facts add up to an impact on a specific date in the near future. They add up to a long-term statistical risk that is genuinely concerning over the span of a human lifetime, but not on the span of a single week. The reason the conspiracy framing spreads so effectively is that the real story does not produce the kind of clear, actionable conclusion that human minds prefer. The real story is, the planet is in a cosmic shooting gallery, the bullets are infrequent but not impossible, the tracking system is incomplete but functional, the response capability is limited, and the probability of any given year being the one is very low. That is not a satisfying story. The conspiracy version, with its specific dates, its named villains, and its imminent catastrophe, is much more emotionally clarifying. It is also wrong. The institutional response to the conspiracy claims has been muted, partly because public denials tend to amplify the original claims. The NEO's office maintains its public-facing database, publishes its routine updates, and answers specific questions when they are asked. The FEMA exercise reports are publicly available for anyone who wants to read them. NASA's Planetary Defence Coordination Office runs a public website with frequently asked questions and explainer videos. The information is out there, in the original form, for anyone who wants to verify it. The problem is not access to the data. The problem is that reading the data requires patience, and patience is in short supply on social media. The other complication is that some of the conspiracy claims contain partial truths. There are real institutional gaps in planetary defence. There is real underfunding of the detection network. There are real blind spots in the daylight sky. There is a real disconnect between the technical risk analysis at NEO's and the public communication strategy of the major news outlets. A skeptical observer who reads the conspiracy claims and then digs into the underlying data will find that some of the criticisms of the institutional system are valid, even if the specific conclusions about imminent impact are not. That partial validity is what gives the conspiracy framing its staying power. We don't need to invent fictional doomsday scenarios when the real data we are waiting on is scheduled to arrive in a matter of days. Part 11. The next radar astrometry update. The most important data regarding 2026 KM3 will not be recorded before it arrives, but as it pulls away. That is the central technical fact about the next several days of observation. The Flyby itself, the moment of closest approach, is not the data collection event. The data collection event is the entire window of time around the Flyby, with the most valuable observations coming after the rock has passed, and is moving away from Earth on its outbound leg. The reason has to do with the geometry of radar measurement. When an asteroid is approaching, the radar signal bounces off the side of the rock that is facing Earth. As the rock passes, the radar can see different parts of its surface, because the geometry between the radar dish and the rock is changing rapidly. As the rock moves away, the radar continues to see the receding face. The full set of observations, across the approach and the departure, gives the planetary scientists a three-dimensional view of the rock's shape, rotation, and surface properties. More importantly, the observations across the full flyby window give an extremely precise measurement of how the rock's orbit has been altered by the encounter with Earth's gravity. The pre-flyby orbit is known from the optical observations collected over the past several months. The post-flyby orbit will be known from the radar observations collected over the next several days and weeks. The difference between the two orbits is the gravitational deflection caused by Earth. That deflection is what determines the new Earth MOID value. The deflection is what determines whether the rock passed through any keyholes during the encounter. The deflection is what determines the long-term threat profile of 2026 KM3 for the next several decades. The Goldstone Solar System radar in California is the primary instrument for the post-Flyby observations. The Deep Space Network antennas at Goldstone, particularly the 230-foot dish known as Deep Space Station 14, will be focused on the rock during the days following closest approach. The radar will transmit a coded signal in the X-band frequency range, bounce the signal off the asteroid, and receive the return signal a few seconds later. The round-trip time gives the distance. The frequency shift gives the velocity. The pattern of the return gives the shape and rotation. Each radar measurement is precise to within a few meters in distance and a few centimeters per second in velocity. After dozens of measurements collected across several days, the orbit of the rock is constrained to a level of precision that no purely optical observation could ever achieve. The post-flyby orbit will be known better than the pre-flyby orbit by several orders of magnitude. If the post-flyby radar astrometry shows a shift of even a fraction of a degree, the entire long-term threat model has to be rewritten. That is the precise sensitivity of the measurement. A fraction of a degree in the orbital plane, multiplied across the future passes of the rock over the next several decades, produces a substantially different prediction for where the rock will be at any given future moment. The MOID number itself is sensitive to small changes in the orbital elements. A shift in the orbital inclination by even a tenth of a degree can change the MOID by tens of thousands of miles in either direction. The published update from the senior's office, when it comes, will include the finalized orbital calculations. This set of precise geometric coordinates completely redefines the asteroid's path through our inner solar system, permanently locking in its new trajectory. The second is the new Earth MOID value, calculated from the new orbital elements. The third is the updated list of future close approaches, with their projected distances and dates. The fourth is the updated impact probability assessment, expressed as a value on the Palermo Technical Impact Hazard Scale and the simpler Torino Impact Hazard Scale. The Torino scale runs from 0 to 10. A 0 indicates no risk. A 10 indicates a certain global catastrophe. Most catalogued near-Earth objects are at 0, including 2026 KM3 in its current pre-flyby assessment. A few objects have briefly been rated at 1 or 2, indicating a low but non-zero probability of impact that warrants public attention. Only a handful of objects in the history of asteroid tracking have reached 3 or higher. The post-flyby update for 2026 KM3 is expected to remain at 0 on the Torino scale, but the Palermo scale, which measures relative risk against the background rate of impacts of similar size, may show some variation. The Palermo scale is logarithmic. A value of 0 means the object's impact risk is equivalent to the background rate for objects of its size. A negative value means the object is less risky than the background. A positive value means the object is more risky than the background. Almost all catalogued objects have negative Palermo values. A positive value is rare and notable. The pre-flyby Palermo value for 2026 KM3 is around -4, well below the threshold for special attention. The timeline for the post-flyby update is roughly 2 to 4 weeks from the date of closest approach. The initial radar observations will be processed within a few days. The preliminary orbital fit will be available within about a week. The refined orbital fit, incorporating all the radar and optical data from the flyby period, will be published within 3 to 4 weeks. The full technical paper, if one is written, may take several months. The waiting period is the part that the conspiracy framing exploits most effectively. In the absence of immediate public communication from NEOs, the social media speculation fills the void. The void is unavoidable, given the technical realities of data processing. but it is also where the misreading takes root. The honest framing of the next few weeks is, the data is being collected, the analysis is in progress, and the answer will be published when the calculations are complete. The data will give us an answer for this specific rock, but it cannot change the larger environment we live in. Part 12. The clock that does not stop. We return to the image of that 110-foot mass of iron and stone, no longer approaching, but silently pulling away into the vacuum of deep space. The rock has done what it was always going to do. It has crossed our orbital neighbourhood, brushed against our gravitational field, and continued on its way. The June 9th pass is in the rear view now. The data collection is in progress. The numbers, when they come, will be what they are. There is a particular quality to the silence after a close approach. The cameras at Goldstone are still pinging the rock. The CNEO's office is still updating the orbital elements. The Catalina Sky Survey is still scanning the sky for the next object. The work does not stop. But the public attention has shifted elsewhere. The news cycle has moved on. The names of the next stories are different. The asteroid, having failed to deliver the catastrophe that some online voices predicted, becomes a footnote in a database, accessible to anyone who knows where to look, ignored by almost everyone. The institutional system has done its job, in the sense that it can be done within current capacities. The rock was detected before the flyby, the orbit was calculated, the radar tracking was scheduled, the flyby was monitored, the post-flyby data is being processed. None of this required heroics. None of this involved last-minute deflection missions or emergency evacuation orders. It was the routine work of a small network of professionals doing what they have been trained to do, with the equipment they have been given, on the budget they have been allocated. The larger picture, the one that the routine of this single flyby does not address, is the one that the planetary defense community lives with every day. The asteroid population in the inner solar system is vast. The catalogued near-Earth objects number in the tens of thousands. The uncatalogued objects in the size range of 2026 km3 are estimated to number in the hundreds of thousands. The rate at which new objects are added to the database is several thousand per year. The rate at which existing objects are removed from concern through orbital refinement is much smaller. The net trend is that the catalogue grows, and the work of monitoring grows with it. Some of those uncatalogued objects are on orbits that bring them close to Earth. Some of them have Earth MOID values smaller than the 0.0126412 of 226 km3. Some of them are larger than 110 feet. Some of them are approaching from the daylight side of the sky, invisible to the current network until they pass. The mathematical certainty is not that an impact will happen on a specific date. The mathematical certainty is that, given enough time, an impact will happen. The probability per year is low. The probability over a century is meaningful. The probability over a millennium is essentially 1. That is the cosmic shooting gallery that the planet sits inside. Every orbit Earth makes around the Sun brings us through a region of space that contains thousands of small rocks, hundreds of large rocks, and an unknown number of objects that have not yet been seen. The atmosphere absorbs most of them. The small ones, the dust and pebbles and the occasional basketball-sized fire. The medium and large ones, like 2026 km3, do not get absorbed. They either miss or they do not. The infrastructure on the ground beneath this sky is fragile in ways that are difficult to fully appreciate. The electrical grid depends on a network of transformers, substations, and transmission lines that were designed to handle weather, not airbursts. The water systems depend on pump stations that require continuous power. The food supply depends on long-distance trucking, which depends on highways and fuel and refrigeration. The medical system depends on hospitals that operate within thin margins of supply and staffing. Any major disruption to any of these systems, even a regional one, would cascade into the others. A 10-megaton airburst over a metropolitan area would not just kill the people in the immediate impact zone, it would disable the systems that the surrounding regions depend on, and the recovery would take years. The planetary defense community knows this. The FEMA exercises are designed to surface exactly these cascading failures. The reports do not get widely read. The recommendations do not get widely implemented. The funding does not get substantially increased. The work continues, quietly, with whatever resources are available, because the work has to continue, regardless of whether the public is paying attention. For the viewer watching this script on a television in a quiet living room, the practical implication is small. There is nothing to do tonight. There is no preparation to make for tomorrow morning. The June 9th Flyby will pass, and the post-Flyby data will eventually arrive, and the answer for this specific rock will be what it is. The next rock, when it comes, will be discovered by the same network, or it will not be discovered at all, and either way the response will be what the system is capable of delivering. What there is, instead, is awareness. The awareness that the orbital geometry of the inner solar system is not benign. The awareness that the work of monitoring and tracking and modelling is being done by people who will never be famous, with equipment that will never be glamorous, in offices that will never make the evening news. The awareness that the numbers in the database are not. They are the difference between knowing what is out there and being surprised by it. As the rock recedes into the dark, radar pulses continue bouncing off its surface, while technicians in Pasadena and at Goldstone silently log the final returns. The orbital fit is tightening with each new measurement. In a few weeks, the post-flyby orbit will be known to a precision better than the pre-flyby orbit was. The Earth MOID number will be updated, the future close approach dates will be recalculated. The work, as it always does, will move on to the next object. Above the houses, above the power lines, above the lights of the small town and the big city alike, the sky tonight contains the same orbital crossings it has contained for billions of years. The crossings do not announce themselves. The geometry does not need an audience. The rocks do not know that they are being watched, and they do not care. They follow their orbits, as they always have, on paths that are determined entirely by gravity and by the initial conditions of their creation in the early solar system. Somewhere out there, beyond the range of any current telescope, the next rock is already on. It has been on its way for thousands of years. It will continue to be on its way for thousands more, until the moment its orbit and ours coincide at the crossing point. When that moment comes, it will come without ceremony, without warning, without preference for any city or any country or any time of day. The system will do what it can. The numbers will be calculated. The radar will ping. The database will update, and the planet, fragile and busy and largely unaware, will continue to turn beneath a sky that has never stopped watching back. The clock does not stop. The watch continues. Stay tuned.